Welcome back, AP. We have 3.3, which is formula and molecular weights. So with formula and molecular weights, remember weights is looking at that gravitational force. We use AMU, not grams, because it doesn't say the word mass. When you're doing this calculation, you want to use the periodic table fully. Don't round any numbers from the periodic table. So first, let's look at the difference. Formula versus molecular weight. We already talked about the weight is AMU, so both using AMU. But with formula weight, it's ionic compounds. So metals, nonmetals, polyatomics, you crisscross, you balance the charges. With molecular weight, it's with molecules, nonmetals only, okay? Is the calculation different? No, it's just how it's classified. So if I had salt, sodium chloride, I have one sodium, one chlorine, add it up. And remember, when you're adding sig figs, it's the least after the decimal. So it really helps to line up the decimals and then add it up so you keep those two places after the decimal, okay? You're going to find out that 99% of the time, molecular weight, formula weight, molar mass, they all have two numbers after the decimal. It's very rare that you would actually have three after the decimal. Molecular weight for sugar, glucose, is you have 6 times 12.01, and you have the 12 times 1.01. Now, I do know the periodic table for hydrogen that AP gives you does say 1.008. I'm used to 1.001. I'm sorry, 1.01. Either one is fine for AP. 12.06, 12.12, add it all up. You just need to make sure you have those two numbers after the decimal. And because we're talking about weight, we have AMU. Notice the answer. I always chant this in class. Number, unit, chemical. So make sure you always in that answer have your number, unit, and chemical. And please, when it comes to calculation, box those answers, okay? Now, how is weight different from mass? Well, the word mass is a base unit, so grams. Is the calculation different? No. It's just one is grams, one is AMU. So the definition of molar mass, it's the mass in those grams that equal 1 mole of that substance. Okay, so if I had sodium chloride and I want the molar mass, well, instead of 58.44 AMU, I say 58.44 grams. And it equals that 1 mole. Remember, the abbreviation for mole is MOL. You need to get used to a different unit for molar mass, which is called grams per mole. And you'll see when we get to some sample calculations later in this chapter. But molar mass could just be grams, or it could be grams per mole. So when you find the molar mass, you add up all the atoms that are in that formula. So be very careful when you have subscripts like diatomic nitrogen, 2 times the mass of nitrogen, which on the periodic table is 14.01 grams. And because it's 2 times that number, you need to keep those 2 after the decimal. Because the same thing as saying 2 times 14.101 is the same thing as saying 14.01 grams added to 14.01 grams. You keep those 2 after the decimal. 28.02 grams or grams per mole. Either one is fine. Okay? So reminder, ladies and gentlemen, do not round any numbers on the periodic table. We should be properly using the actual mass of hydrogen that's listed on the periodic table. AP likes to edit the number for hydrogen. Either one is fine with me, but we're going to try to start using that 1.008 since now it is listed that way on our new periodic table. So one more time before we get to the next category, formula weight, molecular weight, molar mass, they're all calculated the same way. We just use different units, okay? So to go with this category is something called percent composition. Percent composition from formulas, we sometimes call it percent by mass, percent composition. It's like calculating your grades. So when you would calculate your grades in class, the number that you got over the total, and then you times it by 100. It's the same calculation. We're just now using grams. So because it's called percent by mass, we're going to be using grams. Percent composition is based on mass, not how many numbers are present. And I want to make sure you understand this concept that I'm mentioning. H2O has 2 hydrogens for every 1 oxygen. Now you think that because it has 2 times as many hydrogens as oxygen, you think that the majority of the mass is coming from those hydrogens, and it's not. So that's why I'm trying to get to this point. Percent composition is based off the mass, not how many atoms you see. I could have 10 atoms of hydrogen, but the majority of the mass is still coming from oxygen, and I'm going to prove that point with this first example. So how do we calculate percent composition? So with water, the majority of the mass is actually coming from oxygen. And how do I prove that? So with percent composition, we need to take the mass of each element and divide by molar mass. But this mass of this element, it's the total mass. So if you have 10 hydrogens, you need to take into account those 10 hydrogens. So the total mass divide by molar mass, so grams divide by grams, they're going to cancel. We want them to cancel because this calculation is called percent composition. So when you take grams divided by grams times 100, and we do not use this for sig figs, this is just to move the decimal 2 places. And then I'm going to get a number in percent. And that tells me how much of that element makes up that compound. Now you always want to check your work. You know how Rodriguez is always beating that concept in your head. Always check your work, because in life, ladies and gentlemen, 100% is all you can have. You can't create matter. You want to make sure that you give yourself a little wiggle room, plus or minus about 0.5. So if you add your numbers up to 99.5 to 100.5, you're good. Why would you need that wiggle room? Is because of rounding and sig figs. Sometimes those 2 concepts always screw it up. Okay? So let me prove to you what I'm trying to say about percent composition is based off mass, not the total numbers. So percent composition of water, H2O. So first, the steps. Number 1, we need molar mass. So I'm going to make some notes over here. You know Rodriguez always shows you the rules. So number 1, calculate molar mass. Okay? So I have hydrogen times 2. I have oxygen times 1. And we're going to use the actual number that's on the periodic table that AP gives us. We want mass, not weight, so we're going to go grams. So we're going to multiply this out. Let's get those calculators out. Let me get mine out too. 2 times 1.008, and I get 2.016 grams. I got to keep those 3 after the decimals because I'm just multiplying by 2. Oxygen we know is 16.00, so 16.00. And notice I said sometimes molar mass has 3 after the decimal, but when we add this up, we do have to cut. So 2 plus that 16. So I'm going to get 18.016. But because of sig figs, I'm going to cut, and then I need to round that number up. So my molar mass is going to be 18.02 grams. And don't forget the chemical in the back. Step number 2, I'm going to use that formula. You're going to calculate the percent for each element. So I'm going to take the total mass, and I'm going to divide it by 18.02 grams. Now, if you leave yourself a little bit of space in between, like for example, since I have some space right here, you can just put it right in between. Okay? So let's do that instead, because then that way you could see what happens with the sig figs and the units. So 18.02 grams. So you want to probably leave yourself about a line of space. Grams divide by grams. Grams divide by grams. But we're going to times it by 100. So in each one of these, my sig figs are going to be based off 4. There's 4 on top, 4 on the bottom. So 2.016 divide 18.02 and times 100. So I'm going to get 11.18. But we're going to round that to 19. Number, unit, chemical. So water, 11.19% of water is hydrogen. Okay, so even though you have 2 atoms of hydrogen, the majority of the mass is coming from oxygen. So we're going to take that 16 divided by 18.02 times 100. And you're going to get 88.79 and then percent. So now here comes check your work. Add up those two percentages. Now we're going to box these answers because these are our answers. But let's check to make sure it equals 100. 11.19 added to 88.79. And I get, because of sig figs, 99.98. And that's okay, because that sig fig right there, I'm in that range of 99.5 to 100.5. You're good to go. So I see right there, sig figs and rounding kind of screw it up. So the majority of water, that's the mass that is contributing mostly to water. So be very careful by making predictions. Just because you have 2 hydrogen atoms doesn't mean that's the majority of water. Let's do another sample calculation. What if you don't have the formula? So potassium and carbonate, that's an ionic compound. So I need to balance some charges. Potassium's +1. Carbonate's a polyatomic, CO3 -2. Do a little crisscross to make it neutral. So K2CO3. You're going to do the exact same thing. So K, I have 2. Carbon, I have 1, and oxygen, I have 3. Okay, so we're going to multiply it out. Potassium, according to our table, 39.10, and carbon, oops, I even told you guys to leave some space, and I didn't even leave any space. So let's give a little distance here. Carbon, 1, and then oxygen, 3. So carbon, 12.01, and we already know oxygen, 16.00. So you're going to multiply this out, divide it, and what are those percentages for your formula? Okay, so you guys do that. And let me show you one more example. This is called a hydrate. So calculate the percentage of oxygen in barium chlorate hexahydrate. So barium +2. Because this is an ionic compound. I see a metal and a polyatomic. Chlorate, ClO -1, or actually ClO3 -1. So when I crisscross that, I get Ba. Now because this 2 comes over, I got to crisscross, and I got to use some parentheses. So ClO3, parentheses 2. Now let's talk about this hydrate, because we did talk about this in chapter 2, and a hydrate is an ionic compound that has water added to it, but it's still in a solid crystal form. These are these beautiful crystals. We did this lab with the blue crystals. We just used copper sulfate instead. When you see this hexahydrate, hexa is a prefix for 6. Hydrate means water. Just like when someone tells you, hey, go hydrate. That means drink some water. So what you do is you add that 6 waters to the end of the formula. But in between the formula, you add a dot. Okay? Now I know, ladies and gentlemen, you see that dot and you're thinking math, that means multiply. But in chemistry, that dot means add. Okay? So we're going to take the molar mass of the barium chlorate, and we're going to add it to the molar mass of 6 waters. And because we already know the molar mass of water, we know the molar mass is 18.02. We don't have to solve that again. So we're going to list it. So Ba, I see 1. Chlorine, because of the parentheses, I see 2. And for the oxygen, 3 times 2 is 6. And I'm going to give myself some space. And then the water, I'm going to say 6 and then times that molar mass. Okay? So with oxygen, 16.0. With chlorine, according to our periodic table, it should be around, what is that, 35.45. And barium's got a big mass, 137.33. Okay? So when you do all the math, okay, calculate those percentages, okay? And if you do this correct, as I'm checking my work, the one that should have the highest percentage is the oxygen. So this oxygen percentage, it should be the highest if you do this right. Should be around 46%, okay? To double check your work for potassium carbonate, if you do this right, the potassium should have the highest percentage, and it should be around 56%, okay? See you on the next one.